In this video, we will learn a bit more about the dot product and how to visualize it. First, however, we will start with how to construct a unit vector. So far, we have seen three unit vectors, I hat, j hat, and k hat. However, remember that the meaning of a unit vector is simply any vector with length 1. So, supposing I have a vector r, and I want to construct a unit vector that has the same direction as r, but obviously has magnitude 1. How do I do it? What I must do is, since r has the correct direction, I simply need to scale it until it has the correct length. So I take the vector r and divide it by its magnitude. Since I have divided the vector by a number, I will scale its length appropriately, and this gives me a unit vector with length 1, which still has the same direction as r. Remember that scalar multiplication doesn't change the direction of r, it simply changes the length. Notice the hat symbol on top of r. The hat symbol here is used to refer to any unit vector. So r hat is a unit vector pointing in the direction of r. I hat can also be called x hat because it is a unit vector pointing in the direction of increasing x. J hat can also be called y hat because it is a unit vector pointing in the direction of increasing y, and so on. Here's an example. Let r equal 1i hat plus 2j hat minus 3k hat. How do we calculate the magnitude of r? We use the Pythagorean theorem. That is square root of rx squared plus ry squared plus rz squared. Again, remember that even if there is a negative component, like the z component here, when you're squaring, the minus sign will go away. So we get 1 plus 4 plus 9, which is a total of 14, and the square root of 14 is the magnitude of the r vector. Remember that the magnitude of a vector can also be denoted by writing the letter for the vector, but without the arrow. Now that we have the original vector and its magnitude, we divide r vector by its magnitude, and this is now a unit vector. If we take r hat and find its magnitude, that simply becomes magnitude of this expression, which becomes magnitude of r divided by magnitude of r, which is 1. And thus, as expected, the unit vector has magnitude 1. Remember that we find the length by using the Pythagorean theorem. So, for example, I hat plus k hat is not a unit vector. Why? Because if I find its magnitude using the Pythagorean theorem, the magnitude becomes square root of 1 squared plus 0 squared plus 1 squared, which is square root of 2, which is not 1. So, when determining whether something is a unit vector, find its magnitude using the Pythagorean theorem. Again, just to give a pictorial representation, if I am given a vector, to construct the unit vector with the same direction, I simply scale down a vector, keeping the direction the same, until it has the appropriate length of length 1. This is how we construct a unit vector. Now a reminder, there are two ways to do the dot product. One is by using the magnitudes of the two vectors and the cosine of the angle between them. And the other is if you know the components of the two vectors using a simple formula of multiplication and addition. Here's a simple question. Keeping the formula for the dot product in mind, what is a vector dot I hat? Using the component formula, we see that a dot I hat is simply ax. In other words, taking the dot product of any vector with I hat isolates the x component of that vector. Pictorially, let's take another look at this. Taking the dot product of any vector A with I hat, which points along the x-axis, finds the projection of the vector A onto the x-axis. In other words, taking the dot product of a vector with I hat, which is the unit vector in the x direction, gives you the projection of the vector onto the x direction. So, given two vectors A and B, we can construct vector B divided by magnitude of B. But this is simply the unit vector. We have taken a vector and scaled it by its length, and now the overall length is 1, and so it is a unit vector with the same direction as the vector B, so I'll call it B hat. In that case, what is A dot B hat? Using the magnitude formula, we find A dot B hat is magnitude of A times magnitude of B hat times cosine of the angle between them. The magnitude of A vector can be denoted as A. The magnitude of B hat is simply 1 because it's a unit vector, and cosine stays as it is. The final result is A cosine theta. But what is the geometrical interpretation of A cosine theta? This is simply the component of vector A along the direction of B. For example, if these are the two vectors A and B, I can project A onto the vector B. Remember, when doing a projection, you draw a line which is perpendicular to the line onto which you are projecting. Here I am projecting onto the B vector, so I draw a line which is perpendicular to the B vector, not perpendicular to the A vector, perpendicular to the B vector. In that case, this is the projection of A onto B. Once we realize that this is the angle theta between A and B, we realize that this length is in fact A cosine theta. Magnitude of vector A being the hypotenuse, this being the adjacent side, with the angle theta between them. So this is A cosine theta. But that is exactly A dot B hat. But what if the angle between the two vectors is greater than 90 degrees? Here C and D have an angle between 90 degrees and 180 degrees. We first create a dashed line that has the direction of D, and now we find the projection of C onto the line of D. Once again, since we are projecting onto the line of D, we draw the projection line which is at 90 degrees to the line of D. Again, this ends up being C dot D hat. the angle between the two vectors is this. And this is the cosine. So we see that if the two vectors A and B point in roughly the same direction, then A dot B will be positive. In other words, the projection of one vector onto the other is a positive projection. If the vectors point in roughly opposite directions, then the projection is negative, and so the dot product is negative. And if the two vectors are perpendicular to each other, then the projection is 0. We can see that in this case, there is a right angle between the two vectors. If I try to project the green vector onto the blue vector, I see that there is in fact no projection, no shadow, except for a dot. To recap, taking the dot product of A with I hat gave us AX, and that was a projection of the A vector onto the x-axis, that is, the line of the I hat vector. So now we know what a dot product is. It is a measure of the projection of one vector onto another. But what do we use it for? We can use it to check if two vectors are perpendicular. If their dot product is 0, then they are perpendicular. We can use it to find the projection of one vector onto another vector. And having found that, we can also use it to find the component of the vector that is perpendicular to another vector. And later on in the course, we will use it to construct scalars from two vectors, such as the scalar work, denoted by W, which is constructed from the force F and the displacement D. That's the end of this video. I'll see you in the next.